Good morning. This is review session for exam 1, and let's call it this one part 1. Exam 2 will be open Friday, July 7th, and will stay available until Monday, July 10th, until 11:59 Eastern Standard Time. That means please plan accordingly. You may take your test at any day or time during that opening window. The rules stays the same. In order to take the test, we are only allowed to have a paper and a pencil. You will have 110 minutes. All questions will be performed on Canvas through the honor log, the same process. And of course, we are not allowed to have any additional help, any people inside the room, or calculators, or electronic devices, notes, websites, textbooks, just ourselves. Okay, let's see what we have. The material for exam 2 are as follow. We did finish chapter 3, starting from section 3.5 until 3.10, and then we also finished chapter 4 from 4.1 to 4.7. And as you can see, we did divide the material, and today's session will focus on this stuff. Chapter 3 and linearization. That's part 1, and then you will have tomorrow part 2. Okay, excellent. That's what we have. We did learn differentiation rules, lots of differentiation rules, trigonometric functions, chain rule, implicit differentiation, exponential, logarithmic, and then a little bit of application, related rates, and linear approximation. That means these are application of the derivative, and chapter 4 is also application of the derivatives, first and the second. Graphing was like the final output of all of the rules. We remember we had nice session. Graphing, you may also review this session, will be helpful. And the big thing is optimization, but that will be later. Okay, let's focus on the basics. Let's focus on the rules. I did type something here. You may notice this is like related a little bit. I mean, chain rule or differentiation rule. Let me check what I'm doing. Okay, let's see. Derivative of x cubed, everybody knows, 3x squared. But when we will have implicit way, when we will have a function or maybe expression, curve, defined in the explicit way, and we still need the derivative. We know how derivative is important. Derivative represents the slope of the tangent line, slope of the curve. That we still have to be able to differentiate, yes, implicit differentiation. That we have to assume that y is a function which depends on x. We do not have direct formula, but we can still differentiate. And you probably remember this. Derivative of y cubed will be 3y squared times y prime. But the more detailed and appropriate notation is dy dx. So we can say it's kind of like chain rule. That means this, we can also call it chain rule. Derivative of the outer function, 3y squared, times derivative of the inner function, derivative of y, dy dx. And that's me, please remember, if we have this, we will have some examples. That's what I did. I collect a couple of questions which they represent the concept in this particular sections, and I will go through to show you, to review with you the concept. Please make sure that you go through all of these questions in this presentation, also solving a sample problems or practice test for extra credit will give you the idea and of the test, and of course the good preparation. Okay, that means please work every day, and the test will be taken on Canvas through the honor log. Yes, we remember honor log. Okay, let's start. What I have. Differentiation rules, even if they were introduced before, we still have to remember them, because talking about the higher level, different concept, we always have to remember the fundamentals. That means that you may pause the video and you can look at these notes of course, product rule and quotient rule. Then what else we had? Trigonometric functions, okay? All of the 6 trigonometric ratios. Make sure that you know the formulas, okay? Then chain rule. In order to differentiate function and its inner function, we will simply multiply derivative of the outer function times derivative of the inner. Yes, we can see f prime, g prime, but f prime, the outer function, still depends on the same quantity, the same inner function. I mean, this is sometimes the most challenged part, which is relatively easy when we practice. Or if we like the Leibniz notation, derivative of y with respect to u times derivative of u with respect to x. Okay, chain rule. And then logarithmic and exponential forms and inverse trick. That's we have to know the top, exponential, natural and the general one, logarithmic. And actually we do not need this, and I think we don't need this, but we have to know inverse sine of x and inverse tangent. Of course, the notation could be arc sine of x, derivative, and arc tangent of x. Okay, let's make sure that we know the formulas, okay? And product and the quotient rule. We remember that was before, but we still need them. Okay, are we ready? Yes. Part 1, we will focus on differentiation rules plus related rates and linear approximation. Okay, that's what I will practice with you, review with my students. Okay, I just list a couple of functions and let's see, we're supposed to solve this page in like 1 minute. Derivative of 7 to the power of x, general exponential function. Exponential function derivative is the function itself times natural log of the base. Done. Okay, derivative of the logarithmic function, not ln, just log base 4 of x. I mean, it will be the same thing, 1 over x and times natural log of 4. When we have, maybe I can say, when we do have a function just natural log of x, everybody knows the derivative, 1 over x. Correct? What else I can add? Let's say natural log of sine of x. Okay, I'm adding a little bit of chain rule. Okay, we have logarithmic function, which is outer function, inner function is sine. That's what we will have. 1 over quantity, sine over x, times derivative of this quantity, cosine of x. Cosine over sine is cotangent, if we like this way. Okay, now inverse sine of x or arc sine, the same thing. Thinking about the same domain, of course. Okay, derivative of arc sine is 1 over square root 1 minus x squared. Okay, and if we like to add, for instance, f of x equals to arc sine, and what we can do, tangent of x. So we can see the input, the argument is not x, is tangent of x. So we will follow the same formula, derivative of outer function, arc sine of quantity tangent. It will be 1 over square root 1 minus quantity squared times derivative of this quantity. And that quantity is the inner function, tan x. And let's maybe simplify. Okay, square root 1 minus tangent square of x and derivative of tangent. You may pause the video and answer, or maybe you're answering in your head, but I can tell you secant square of x. Yeah, make sure that you know everything what I'm saying. And if I'm asking a question theoretically to myself, that's actually the questions for my students, which are listening the session now. Okay, that's something with the chain rule. And the last formula on this slide, arc tangent of x, derivative, oh, excellent. You probably remember sometimes my pen. Okay, arctangent is 1 over 1 plus quantity squared, and it's just x. Okay, couple of helpful formulas. Let's keep going. Okay, okay. That means this question is just testing product and the quotient rule. Is the old concept, but really important because we can't move it. That means we may ask this way, but let's see. We know the product and the quotient rule, but let's see how we can use the graph. We have function f and g provided here. F is pink and g is like blue or turquoise. And we have to find out the derivative of h, let's say h prime, f times g. That's we need a product rule. Derivative of the first function times the second plus first function times derivative of second. Oh, I think something is missing because we need in order to actually use the graph. Let me quickly check what I'm missing. Or maybe let me 1 second. Okay, actually, let's just say h prime at 1 and v prime at 5. We need an exact point, yeah, because otherwise this will be the answer. We may still leave it, but why even we need the graph? Okay, that's we have the formula. That's actually the first step. And now let's say I just pick the value 1. That we have to find out what is derivative of h at 1. Okay, at x equals to 1. This is x, and this is 1. Okay, 2, 3, 4, 5, 6. Okay, and this is also 1, 2, 3. Okay, so now we will need f prime at 1, g at 1, plus f at 1, g prime at 1. And of course, we combining a couple of concepts. Derivative of the function is the slope of the tangent line, or the slope of the curve. If the graph is a line, it's just that line, that slope. Okay, that's me. Let's figure out f prime at 1. The pink function is f, and 1 is here. But this is 2, 3, 4. We need the slope. That means the slope looks like rise is 4 and run is 2. Actually, it's 2, but I just put the ratio form. 4 over 2, okay? G at 1 is just 1, because this is just the value. We can see this is just 1. The blue graph. Okay, f at 1 is 2. We can see this. F at 1 is 2. G prime at 1, it will be slope of this line. And looks like negative 2 over 2, negative 1, slope. Okay, please remember slope. And maybe I can write the final answer. 2 minus 2, actually 0. 0. If I'm not mistaking, 2 minus 2. Okay, and just a quick note for the product rule, we of course may switch the order because addition, yeah, we may switch it. Okay, now let's find derivative of v, quotient rule. Okay, derivative of f times g minus f times derivative of g, and then g of x squared. Now let's substitute 5. That's we will need f prime at 5 times g at 5 minus f at 5, g prime at 5, and then g at 5, the value squared. Okay, let's get all of the values, remembering that prime, f prime, g prime is the slope of the tangent line, slope of the curve at that point. Okay, f prime at 5. That means f at 5 is here, but that's the value, and derivative will be the slope of this line, and slope looks like 1/3, 1/3, negative 1/3. Yes, slope. And the g at 5 is actually 2. Minus f at 5, it's 3. We can see this value. And g prime at 5 is the slope of this line, slope of that, which is 1, 2, 3, 1, 2. 2 over 3. Positive because the line. And the value at g is 2. We will square it. Okay. Negative 2/3, negative 2, because this can be cancelled out, 4. What we can do, we can say 6, 7, 8, and negative 2/3. I hope I didn't rush. Yes, I think it's correct, because this is 6 over 3, 6, 7, 8, 8, negative 8. Thirds over 4, negative 2/3. Okay, that means this is the answer for that one. This is for the h value. Okay, that means just the rule, but using the graph. Okay, excellent. Now find the derivative of arcsine of e to the power of 3x. It's, of course, we don't have to do almost anything. It will be derivative of arcsine. Derivative of arcsine is 1 over square root 1 minus quantity squared times derivative. And this quantity is e to the 3x, e to the 3x. That means we will need 1 minus e to the 6x, 1 minus, this only has the correct, and derivative of e to the 3x is 3 e to the 3x. That means this is the correct answer. Okay, excellent. Okay, oh, I did have this one. Okay, couple of questions, I did solve it for you. So you may cover really quickly the screen. Okay, this one is, if we see the solution of math problems, it's always trivial. But if we don't see, if it's a blank page, then it's a challenge. We know the formulas, but I just wanted to make sure that even if we're testing this derivatives, please remember about the rules, additional rules, product rule in this case, because that red dot, you can see I'm pointing, we never actually print that. That means it's easy to miss that. And you may see I use the product rule, and this is the final answer. Okay. Another one is the quotient rule. Easy. Sine of x, cosine of x minus 1, but you may also pause the video, possibly. Don't look at the solution, try to do on your own and check against my writing. Okay, that's the chain rule. You may also pause the video. And this one, let's do it. Whichever questions are not solved, we will do it together. But all of them are important, and all of them are ready for you to be redone. You can practice. Okay, we have to find the second derivative. Then we need the first derivative, of course, product rule. Derivative of x is 1 times e to the 5x plus x times derivative of e to the 5x is e to the 5x times derivative of 5x 5. Okay, now we can differentiate. Let me possibly copy this. 5x times e to the 5x. Okay, now second derivative. Derivative of e to the 5x is e to the 5x times 5 plus derivative of 5x is 5 times e to the 5x plus 5x times derivative of e to the 5x is e to the 5x times 5. Okay, that means this is the final answer. Lots of 5s. 5x was the inner function. We have e to the 5x, e to the 5x, 10 times e to the 5x, correct? And then 25, 5 times 5, x e to the 5x. Okay, it's definitely a pattern. If we will continue, third derivative, fourth derivative, we can find some pattern, but we will stop here. Okay, and this is good for all of the numbers, exponential functions, domain, all of the numbers. Okay, another question that I prepared. Okay, it's again inverse sine of x chain rule and the quotient rule. Let's try. Let's differentiate. Derivative of arcsine, yeah? Because I can say this is arcsine of the square root of x over square root of x. Derivative of arcsine is 1 over square root 1 minus quantity squared times derivative of this quantity, or derivative prime. And the quantity is square root of x. We will simplify. Now, times derivative, I mean just the function from the denominator, minus function from the top, arc sine of the square root of x, times derivative of the denominator. Derivative of the square root of x is 1 over 2 square root of x, and then denominator squared. Okay, let's see what we have. We will have 1 minus square root of x squared is x, of course, saying that x is positive or equals to 0. Actually, we cannot accept 0 because we do have also square root of x in the denominator, just positive numbers. Okay, derivative, now the green, derivative of square root of x, the same, 1 over 2 square root of x. Okay, times square root of x minus arc sine of the square root of x, 1 over 2 square root of x. Square root of x squared is x. Okay, what we can do, I can cancel this algebraically. And let's just leave it. I think this will be 2 times 2 square root. I can write a little bit higher. 1 minus x minus arc sine of the square root of x over 2 square root of x over x. Okay, let's just leave it. But one important comment is this square root of x we cannot cancel out because that's not algebraic like function, the trigonometric, inverse trigonometric. That's different type, and this is the angle. This is sitting like inside. It's not a product to be like cancel out. Okay, let's leave it. We may still try to get common denominators, but important was the quotient rule, chain rule, and yes, and couple of formulas. Okay. Next one is arc sine of cosine of 2x. This one is just a chain rule, because in order to differentiate, we will differentiate arc sine, which is 1 over square root of 1 minus quantity squared, and the quantity is cosine of 2x. And we can speed up times derivative of cosine of 2x. Derivative of cosine of 2x is negative sine of 2x, and times derivative of the most inner function, 2x times 2. Okay, let's simplify. Negative 2 sine of 2x, that's the derivative of the inner function, 1 minus cosine square of 2x. And we have 1 minus cosine square. We know Pythagorean identity, sine square of a plus cosine square of a equals to 1. Then when we have to solve for sine, it will be 1 minus cosine square of the angle. 1 minus cosine square of 2x. That means this, maybe I can save the room. This will be sine square of the same angle. Okay, and what we see, let's just do it. Square root of sine squared of 2x, square root, and the squared can be cancelled out because everything is positive. We are fine to cancel out sine of 2x. And the entire function can be cancelled out. The answer is negative 2. So nice, so nice. Again, a little bit of rules, a little bit of trigonometric identities, and the algebraic fluency. Okay, quotient rule and the chain rule, maybe I can leave it for you. Oh, let's solve it. We have to find out the derivative of g. First of all, g g prime, but what I would like to do, I would like to use the property that 2 I can place in front. Yeah, it's better to have a constant multiple rather than x squared as an inner function. Okay, that's we can copy constant 2. Oh, actually, okay, I can actually keep it. I can keep that 2 separately. And the natural log of x over x. Quotient rule. Derivative of natural log of x is 1 over x times denominator minus natural log of x times 1, because derivative of x is 1. Okay, and let's simplify. This will be 2, and this is 1 minus ln of x over x squared. And when we substitute e squared, let's see what we will get. Natural log of e squared over e squared squared. 1 minus, and again, this one will be 2 times ln of e to the power of, and ln of e is 1. 2 minus 1 is negative 1 times 2, negative 2 over e to the power of 4. And I believe we do have one option like this. Okay. Okay. Nice quotient rule, logarithmic formulas. Yes, lots of good concepts. Okay, another one. Chain rule. Find the derivative of h, which is defined as a f of g of 2 of x, and h at 5. Yes, at least I have this one. The point, yeah, provided. Okay, no product because it's just the chain rule. Derivative of f times derivative of g and derivative of 2x, 2. But f, outer function, depends on the entire quantity, g of 2x. G depends of 2x and times 2. Okay, that's me. Now let's substitute 5. F prime g at 10, 2 times 5, g prime at 10 and times 2. G at 10 is 2. G prime at 10, oh, it's actually 10. And now f prime at 2 is 8. Okay, 8 times 10 times 2, 8 times 2, 16, 160. 160. Beautiful. Another chain rule, but I solve it for you. Please make sure that you follow this, or you may probably take a little bit different steps, but the final answer we have to match. Another differentiation rules. Let's find the derivative of the function f of x, and the function f of x is defined too complicated. Natural log of x times 1 minus x quantity, 1 minus x to the power of 5, all over the quantity x squared plus 1. Definitely, we will not, like we can see lots of product rule, quotient rule, chain rule. We will use the logarithmic properties first. I mean, when we dividing quantities, yeah, we know that this was the subtraction of 2 logarithms. That's what I use. Log of a minus natural log of b, we can rewrite as a 1 logarithm, and the inputs are divided. Okay. That's good, but still I can do it. I have logarithmic function of the product. If we have a product inside, we can add, we can split for addition. Okay, minus natural log of x plus 1. And you may probably see one more. Actually, what I did, ln of a plus ln of b is 1 logarithmic expression a times b. Okay, that means this is fine, ln of x, and that 5, that exponent can be placed in front. Okay, this one we cannot simplify because when we have 1 logarithmic of addition, that's what it is. Okay, now we're ready to find f prime of x. Derivative of ln of x, 1 over x. Copy constant. Derivative of natural log of 1 minus x is 1 over 1 minus x, and times derivative of 1 minus x, which is negative 1. Now, logarithmic of x squared plus 1, derivative is 1 over quantity x squared plus 1 times derivative of this quantity, 2x. And that's we still have a couple of chain rule. This will be negative, and this will be negative 2x x squared plus 1, and we can leave it like this. Okay, but at least we can do it derivative in like 2 steps, or almost 1. But we use the property of logarithm. Okay, another one. Okay, this one is also important. We have to differentiate natural log of x to the power of x. That we may notice the base of this expression depends on x and the exponent depends on x. That please remember, it's not exponential form and not power form. When we have a to the x, to differentiate, this is exponential. Copy exponential function times ln of a. When we have x to the a, power function derivative is just a x a minus 1. But when we have function taken to the power of another function, how we can differentiate? We have a couple of rules, but we will use the logarithmic differentiation. Okay, I can copy this like that, ln of x to the power of x. Now we will take natural log of both sides, natural log of y and natural log of right-hand side, ln of x to the x. And now I can differentiate. So maybe I can write, I will differentiate with respect to x, both sides, natural log of y, and actually this one, that x, since we have ln, I can place in front, and then I will have that green ln of x. And that's okay. This one, we have just product rule and the chain rule. But what we're thinking, yes, this is of course y. We're still looking for y. I mean y prime, derivative of y, dy dx. Y depends on x. And that's we still have to think about the implicit differentiation, and chain rule. Okay, let's differentiate. Derivative of natural log of y with respect to x is 1 over y times y prime, or dy dx, times derivative of the inner function. Now the right-hand side. Derivative of x is 1 times natural log of ln of x plus x times derivative of ln of x is 1 over ln of x times derivative of ln of x, 1 over x. Okay, we will have y prime over y. This will be natural log of x. We can cancel out plus 1 over ln of x. And we will solve for y prime. I will multiply both sides, ln of x plus times y, and most likely we will need to rewrite y in terms of x. That means y is just the original formula. So the final answer will be ln of x plus 1 over ln of x, and everything multiplied by y, but y is defined as a ln of x to the power of x. Okay. We did manage, we do have derivative of y with respect to x, going through the logarithmic differentiation. Please redo this, please. Don't allow yourself to do this question, this type of question for the first time on the actual test. Not good, not good. But I know that you will practice, okay? And logarithmic differentiation again, x to the ln of x, always pay attention. x to the x. And yeah, that means definitely yes. Oh, definitely not this answer. I can maybe, yeah, definitely not. I did the same way, but you can practice. And tangent to the x over x, I did the same way. You can even see my colors. Okay. And at the end, I did substitute pi over 4, a little bit of unit circle. Okay, we're good with the logarithmic differentiation. Now we also had an implicit differentiation. Let's do this. If you need a break, you may pause the video, go and get maybe a cup of coffee, cup of tea, and come back, okay? Because we need practice. Okay, now we can see we have expression in the implicit way, not explicit, because we will not even try to solve for y and use the explicit way. We will just take the equation like it is, x squared minus xy plus y squared, and we will equals to 7, and we will differentiate with respect to x both sides. We remember that y is a function of x. Okay, derivative of x squared is 2x minus. Now we have product x times y. I will open because it's negative. Derivative of x is 1 times y plus x, and derivative of y, it's y prime, or dy dx. I am using shortcut, dy dx is y prime. Now, derivative of y squared is 2y times y prime. Okay, derivative of 7 of the constant is 0. And we just have to solve this equation for y. 2x minus y minus xy prime, 2y, y prime. I will leave, let me maybe change the order a little bit. Yeah, negative, you notice I distributed negative. That's also could be the mistake. Let me put this 2y, y prime minus xy prime. I copy this and this one, but I put the negative term second. And then I add y to both sides and I subtract 2x. Now I am factoring y prime, 2y minus x. And I will divide in order to get y minus 2x, 2y minus x. But let's see, maybe we have to use algebra. Do we have that form? Actually, we do have the form. Is this one? 2y, that's not good. Okay, because I was also thinking, just in case, if we will factor out negative, like if you will rearrange a little bit different, you may get the answer 2x minus y and x minus 2y. But please notice, this is y prime, they are equivalent. And just switching the sign, Okay, but I actually did the same way, but even if you get this form, it's still correct. Okay, implicit differentiation, the second line, make sure that you're not missing any terms. And now I have another question. It will also require implicit differentiation, you can see, but we have to find the equation of the tangent line. That's mean when we are asked to find the equation of the tangent line, we may use point slope form. We remember that because the point is given to 1, this is 1, this is 2, and we need slope, we need derivative at that point. Okay, slope is the derivative. That means let's figure out the derivative and then we will come back to the equation of the tangent line. Okay, let's differentiate with respect to x this expression. Similar. Derivative with respect to x of them. Okay, derivative of x is 1. Derivative of x squared is 2x times y, and we do have addition in the product. Okay, let me do it. Then I will distribute negative. X squared times derivative of y is y prime. And derivative of 5y squared is 10y times y prime. Derivative of 3 is 0. Let me maybe distribute. negative. Please do not mess up. This one is good. One thing that we may take the advantage of, instead of like isolating y prime, like we did in the previous exercise, I can take the advantage that we're looking for the y prime, at the point 2, 1. That means x is 2, y is 1. Let's substitute and then solve. Because we're not looking for the formula like in the previous problem. Okay, that's we have 1 minus 2 times 2 times 1, 4. 2 squared is 4, y prime. 10 times 1, 10. Okay, we do have 6, y prime, negative. Am I right? This is 6. 1 minus 4 is negative 3. Adding to both sides is 3. That means y prime is 3 over 6, 1/2. We can see a little bit faster. Okay, 1/2 x minus 2. That means the equation is 1/2 x, 1/2 x, 1/2 times negative 2, negative 1, and negative 1 actually is 0 when we add 1 to the both sides. Okay, 1/2 x. That's the equation of the tangent line. Tangent line to the curve at the point 2. Okay. Another one. Okay, that's me. We're good with this one. Rates of change. Let's see. I have the graph. Consider the graph of a distance s. That means this graph is a distance from the origin as a function of time of the certain car at the certain trip. And now we have 3 statements. 1, 2, 3. I mean 3 questions, and each of the question has 3 statements. Only one is correct. Okay, only one is correct. A, B, or C for each of them. Okay, over the interval between 0. That means this interval, and between 0.5, between 1/2 and 1. Okay, that's what we know. Velocity is decreasing, velocity is increasing, velocity is negative. Velocity, okay, let's actually, when we have this position function, that means this is distance, position, distance. Then velocity, v of t, we remember velocity is the rate of change of the distance. Velocity is the rate of change of the distance with respect to time, which actually is the derivative, yes, derivative of this. Or graphically we can say tangent line, yes, tangent line, or actually slope of tangent line at the particular point. That's in what we can do. If you see this type of question, velocity, you can think slope of the tangent line to this graph. Okay, that means slope of the tangent is decreasing. Let's see. This is, for instance, slope, because I'm only investigating that. And then that slope is quite steep. And then again, another slope is getting less steeper and almost horizontal. That means the slopes are actually getting smaller and smaller. That means they are not increasing. They are positive lines. That means they are not negative. Slope is decreasing. Okay. I hope we're good. That's one tangent, another, and almost horizontal. Okay, let's do the same between 1.5 and 2. 1.5 and 2. Okay. Slope of the tangent. Oh, no. We have to, let's actually see. Slope, it's this way of the tangent. Then it's more negative, but then again, it becomes almost 0. That means it's kind of like decreasing and then increasing. But all of the slopes has a negative value. That means I think this is the correct, because it is increasing and decreasing, at some point, that means we cannot say it's just increasing. Yeah, it's not monotonic, the slope of the tangent, because we can see this one, and then again it's less steep. But all of the lines has negative slope, okay? And the last interval between 2 and 2.5. Velocity, which is slope of the tangent to the distance function. Increasing, decreasing, negative. Let's see. Definitely not negative. Slope, 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 not negative. And we're starting from almost 0. I mean 0, exactly at 2. And then it's getting steeper and steeper. That means I think is increasing. Do you think it's increasing? And it attains some maximum, like inflection point, but it is increasing. Okay. So we have 3 different intervals. I can possibly remove this and you can maybe investigate, okay? You can investigate these slopes, but please remember, I did investigate the slope of the tangent line, okay? You're not gonna miss this type of question. Okay, and we have related rates. Let's, just maybe 1 or 2 related rates and 1 or 2 linear approximation, and we will be done, okay? But again, you may take a break. You may take a break, okay? I know that is review session, but we're practicing every day. You can maybe come back. This video is provided for you, and you can do whatever works for you, okay? Okay, what we have, let's see. The water is pours into a fish tank at the rate 3 cubic feet per minute. How fast is the water level rising if the base of the tank is a rectangle of the dimension 2 by 3 feet, which we can actually see. Okay, that means definitely the purple on this picture is the water. That means this volume, this amount, the rate of change of the volume with respect to time of that purple, of that water, it's changing with 3 cubic feet per minute, okay? How fast is the water level rising? That means this is height. We're looking for dH dt, okay? Okay? So we need the relation between V and H, and this will be just the volume, the formula for the volume, length times width times height. Length and width is not changing. So we can see it's a little bit different question than the cone and so on. We can definitely use 3 and 2, because if the quantity is changing, then it's always the function of time. 3 and 2 is fine. That means 3 times 2 times h, 6h. This is the good relation, but now we have to differentiate. Derivative of v with respect to time, dv dt. Derivative of 6h will be 6 times dh dt. Okay, and now let me maybe dh dt, it will be 1/6 dv dt. And I can write here dh dt, the rate of change of h, of height, with respect to time is 1/6 times 3. The final answer is 1/2, and it's just the distance over the time, feet per minute. I hope the units are fine, okay? You can probably do even faster, okay? But I just did the formula, that's we need the relation, then we will need the relation between the derivatives, and then substitute everything. Really nice and good exam type question, because it's quick and still testing related rates. Another one that I have, let's see. A kite 6 feet above the ground moves horizontally at the speed 2 feet per second. At what rate is the angle between the string and the ground decreasing at the moment when 100 feet of string has been let out? Okay, that's what's the scenario. That's the ground, and this is the kite. I don't know if that's the good. It's flying, and we know that this is 60. Now, that's the string, that's the string, that's the string, that's the string. If this is, so we can see the angle is definitely decreasing. So what I will do, you may look at this, I will just draw, I will capture one moment because it's still, I will say this maybe. Okay, this is that kite. It's above because it's flying horizontally. That's good. Horizontal is not changing. 60 feet above the ground, that 60 is not changing. And that dotted distance is the distance how the kite is changing with respect to time, which I can like put down. Yes, I can make the projection on the ground. That means this distance x is the same like this one, starting from here. It means that x is changing because this is the speed of the kite with the 2 feet per second. Okay, that's the speed of the kite. Okay, yes, we have x, we know how x is changing, we have 60, and okay, we have that string. We don't know the rate of change, but we know some information because now what we're looking, what rate is the angle, d theta, dt, question mark, at the moment that s is 100 feet. But we know that s is not 100 because as I let the string out in second later, it will be longer, 101, 102, 103, 4, and so on. Okay, that means s is a function theoretically of time and x is the distance behind the kite. Okay, we need the relation because we have x, information about the x, and we need the rate of change of theta. We have to connect them. We will use some trigonometric ratio since we see the right angle and the theta. I mean, we see the right triangle. That's what I was going to say, right triangle and the angle involved. That means 60 and x, we may use tangent, cotangent, maybe cotangent. Cotangent theta will be x over 60. I did use cotangent because then I have x on the top. It will be easier derivative. Okay, it means now I can actually, we can do this way. Okay, that's the relation. Let's differentiate. So we will differentiate, I can maybe say with respect to time, cotangent theta, and we will differentiate with respect to time x over 60. You can still use tangent, but derivative of 60 over x will be one couple of steps will be required. X on the top means is x to the power of 1. X in the denominator means x to the negative 1. Then you can think about the power rule. Okay, derivative of cotangent is negative cosecant square theta times d theta dt. Chain rule, implicit differentiation, or whichever we will call it. Now, derivative of 160x is 160 times derivative of x, dx dt. Okay, and we're looking for d theta dt. We can have 160 now. Now I can substitute dx dt is 2, and we will divide. We will divide both sides by negative cosecant. Negative cosecant square theta. Okay, let's simplify a little. We still need theta. Maybe that negative I can put in front. 60 divided by 2 is 30, because that negative has nothing to do with the square. If this will be squared, it will be not there. That's mean negative, and makes sense, negative because it's decreasing. Yes, we know as kite will fly away, the angle is almost 0. Okay, actually reciprocal of cosecant square is sine. That means it will be sine square theta. We still need theta. We need theta, or we need sine. But we have to use that 100. Maybe I can draw this situation, maybe here. Okay. If that string is 100, this is still 60, we can see we are a little bit lucky. Sine theta is 60 over 100, but this is the situation exactly at the moment when the string is let out by 100. I mean, we don't even have to calculate. We can just say this is, we can cancel out 3 over 5. Yeah, we don't have to use the angle. We can just substitute sine theta. Right? That's it. Let's see if we can get the final answer. The rate of change of the angle is negative over 130, and sine theta is 3 over 5, but squared. Am I right? 60 over 100, 6 over 10, 3 over 5. Okay, that's mean what we have. Negative 3 times 3, 30, 5 times 5. We can divide by 3. That's mean we will have negative 3. 5 times 5 is 25 and 0, because this will be 10. Okay, negative 3 over 25, and since its angle is radians per time unit, and time was in second, I mean this is the final answer. Okay, I can just do it for you this way. Okay, and we may see all of the answers. We do have that answer. All of the answers are not negative, because is that the magic word? Decreasing. Decreasing indicate that all of them are negative. Yes. When we see decreasing, we have to think they are negative. Okay, that's the correct answer. Okay, and then I have another one, but I did solve it for you. Please pause the video, cover with your hand or cover with your like a notebook, and just look at the question. Don't even look at the options, and solve it. Try to get that answer. Okay, I will be so happy if you will get the answer on your own. Okay, and now I have I think two or three linearization. Really simple, really basic, and we will be done. That's part one. Then pay attention for the part two. Okay, linearization. Find the linearization for the function cosine of 2x at pi over 4. We remember that it's just a tangent line. But point slope form, I can rewrite that way, and that's point f of pi over 4 plus f prime at pi over 4 x minus pi over 4. Okay, let's see. Function is defined as a cosine of 2x. Value of the function at pi over 4 will be cosine of 2 times pi over 4, pi over 2. Oh, actually 0. Cosine at pi over 2 is 0. That means this will be 0. Now we need the derivative. Derivative of cosine of 2x is negative sine of 2x times 2. Now, derivative at pi over 4 is negative 2. Sine of 2 times pi over 4, pi over 2. Sine at pi over 2 is 1, negative 2. Negative 2, okay. That means this is linearization, which is just the tangent line, is negative 2x. Negative and negative is positive. Pi over 4 times 2, pi over 2. And I see that answer. But please remember, if you will forget y minus y1, slope x sub 1. Yeah? The y sub 1 is the value of the function. That means this will be f of pi over 4. This one is slope, f prime at pi over 4 minus pi over. You may notice it's the same thing. Yeah, just to make it easy. Okay, that means one question may ask just for this equation. Now I have another question, but I solve it for you. Also, cover the solution. Don't look at the solution and try to solve it. Yeah? No calculators, of course. And okay, I have this one. This is the last one, and I also have a bonus question. Okay, just for you to to ace it, your midterm too. Okay, use the linearization to estimate square root of 11. We remember this type. A little bit slim instruction, But we know we have to approximate function, value square root. That means our function is square root of x. The closest number, closest number to 11, and the number that we do have rational value of the square root, it will be, I'm guessing 9. Square root of 9 is 3. That means let's find the linearization of square root of x at 9. F at 9, f prime at 9, x minus 9. Tangent line. Square root of 9, derivative of the square root is 1 over 2 square root of 9, x minus 9. Okay, that means the linearization, it will be 3 plus 1, 6, x minus 9. And I can leave it that form. I will not distribute since we're doing the approximation. Now, function square root of x can be approximated by the linearization. Yes, x minus 9. Now, square root of 11. We can just approximate by linearization, substituting to the equation. That's what we have. 11 minus 9, we're going 2 units away. 1 6 times 2 is 1/3. 3 and 1/3. And we can leave it like this. Yeah, this is 1/3. Yes, 3 and 1/3. That's it. Square root of 11, 3 and 1/3. And if we like to see if the approximation is like good, or just in case if we will ask for the overestimation or underestimation, that's when we use this is linearization tangent line. That means this is that tangent line. Yes, linearization 3 plus 1 6 x minus 9. And we approximated 11, not by taking this, by taking that blue value. Right? This one, blue value. It's a little bit above, yeah, because the tangent line is above. We overestimated a little bit. Okay, but it's still good approximation because we're not going away. 2 delta x2, maybe it's a little bit too far, but the line, the curve doesn't have a big curvature. Yeah, it's almost flat. That's probably the tangent line will be even closer. Yeah, my graph is a little bit maybe too high. Let me just put 3. Okay, overestimated, but I think if we will find the actual value, will be extremely close, and we're not looking for any error. Okay, and then that's everything for the part 1, but I do have this question, which I found really interesting and might be helpful, which theoretically, this question belongs to chapter 4. But let's just do it, and then I will let you go. Okay, the graph of the first derivative is provided. That's what we see is the graph of the first derivative. Important part, first derivative of the continuous function. That means all of the x's are in the domain of the function. Now, we have to answer this. On what intervals is f increasing? At what values of x does f has a local max and local mean values? And x coordinates of the inflection points. Okay, excellent. I think first of all, this is derivative. Derivative is 0 here, 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 here. And yeah, this will be the end point. Yeah, that means that's the zeros. Also, derivative is undefined at 6. If the derivative is undefined at 6, at some point, and function is continuous, 6 is in the domain. Yes, that means all of the x's are in the domain. Then this is also a critical point. That means all of the red dots are the critical points. Yeah, I can maybe say, what I can say, critical numbers. The derivative is 0 at wherever x, graph is intersecting, I don't like let me put this one, f prime of x at -5, -1, let's say 2.5, 5, and 7. Right? That means derivative is 0. And now derivative is undefined at 6. That means all of them are critical numbers. All of them. Okay, all of them. Actually, I didn't. Let's maybe do above. That means I can put -5, -1, 2.5, 5, 6, and 7 on the number line. Now we can test the sign of the first derivative, the graph that we see. If the graph is below, yes, below, it's negative. If the graph is above, it's positive. That means all of this is negative. Negative. Between -5 and -1 is above, positive. Between -1 up to 5 is negative, negative. Between 5 and 6, positive. Between 6 and 7, negative. And after 7, positive. Yeah. Now, what we know about a function, we don't see the function, but we know the sign of the derivative. Function is decreasing, increasing, decreasing, decreasing, increasing, decreasing, increasing. That we can nicely see. I can maybe take local minimum, local maximum, local minimum at 5, local maximum, local minimum. Actually, I would like to, I don't have extra, let's duplicate this, but let me, okay. Oh, wait, wrong. Okay. Where am I? That means this is this. And let's indicate, or maybe I can say that here, local, okay, local minimum, right? That means this will be at x -5 will be local minimum. Then at -1 will be local maximum. We can see this. At 2.5 is nothing. It's horizontal tangent because derivative is 0, but no extreme values. At 5, it's local minimum. That means no extreme values. Log at 5 is local minimum. It's like a... At 6, this is interesting, local maximum. And at 7, local minimum. Okay? And the increase, the interval of increase, wherever is the plus, increasing between -5 and -1, and then increasing between 5 and 6, and increasing after 7, from 7 to 10. Yes. If the graph is positive, the graph is positive of the derivative, positive, positive, positive. That's the intervals of increase. Yeah, the green intervals. Okay, beautiful. That's, we did part A and part B. Yeah, that's the intervals of increase, wherever I make this green lines. And what are the x coordinates of the inflection points? That means inflection points are the points where the second derivative is changing the sign. Let me do on this the next one. Second derivative, that's we need second derivative to be 0 or the second derivative to be undefined. You have to figure out, and then second derivative must change the sign. That means now, if we're looking at derivative, and if this graph, yes, if this graph, now it's a little bit different, is increasing. Yeah, that means this graph is increasing. This is the graph increasing. Its derivative, which will be the second derivative, is positive. Okay, increasing. That's the graph. Its derivative, it's positive. Increasing. This is the graph. Its derivative is positive. And then increasing, its derivative, which is the second derivative, is positive. Okay? Now, where this is decreasing, this is the graph. Its derivative, which respectively will be the second derivative, negative. Second derivative, negative, second derivative, negative. So now we can see second derivative is changing the sign here, 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 and here. Yeah, and that's the potential inflection points. Yes, the inflection points are at -3, x equals to 1, x equals to 2.5, maybe 2.4, and then x equals to 4 and 9. Okay, I mean that's, and second derivative is defined everywhere. What about 6? 6, probably the second derivative is also undefined, but second derivative is not changing the sign. Yeah, maybe we can have like a second derivative positive. That means function is concave up, concave up. That means this is not an inflection point. Yeah, if we think about the concavity, but that's all of the points for the inflection points, all of the x values for the inflection points. Okay, please redo the last question. Please rethink about this last question, and not even mentioning, please enjoy all of the differentiation rules plus the related rates and linear approximation. If you will be confident with this, you will be good. Every day counts. Please practice, and good luck at your midterm too. Thank you.